Hello, my name is KyoungBok. In this session, we will introduce Gravty. It is a graph database system built for line timeline. I will briefly explain what a graph database is and talk about details of Gravty, what it is, why we made it, and how its architecture is designed to meet our needs. And Mr. Hoonmin will talk about the things we've done to use Gravty more efficiently. Before going into the details about Gravty, let me briefly explain about graph databases. Wikipedia defines a graph database as follows. Sounds complicated, but you just need to remember two things. First, a graph database is a storage that stores objects and relationships. Second, it provides graph search capabilities. Here, each line represents a vertex. Each line that connects them is on edge. You can see who is a friend with whom and who likes what. A graph database stores relationship data in a graph structure and lets you run queries and get results quickly. These are some of the early adopters of graph database technology. Facebook and Google adopted the technology to social graph and page rank. Walmart and eBay use it for their product recommendation system. Nowadays, line services have to deal with all kinds of fast-growing relationship data. To store, process, and query numerous pieces of data more efficiently, we built our own graph database system and named it Gravty. The name comes from the physics term gravity, as gravity represents the force that attracts all things toward the center of the Earth. Our graph database Gravty represents a core center that attracts all data with a relationship. As you can see here, line timeline alone creates, stores, and processes billions of objects and relationships. This large amount of data is the source that helps us discover meaningful relational information. For example, line timeline leverages this information for social graph, post ranking, and post recommendation. Gravty is, in one sentence, a scalable graph database to search relational information efficiently by searching through a large pool of data using the graph search technique. Service needs can change unpredictably, so it is crucial that we have full control over everything. Keeping this in mind, we consider the requirements of Gravty in three aspects. Firstly, Gravty should be easy to scale out to support ever-increasing data. Secondly, Gravty should be easy to develop for developers. Thirdly, Gravty should be easy to use at the client side. So far, I gave you the overview of Gravty. Now, let's take a closer look inside of Gravty. Gravty consists of a graph database framework area based on Apache Tinkerpad and a data storage area based on Apache HBase. Gravty uses Tinkerpad as a graph database framework. Currently, Gravty only includes OLTP functionality. Because we use the Tinkerpad, we can either use Gremlin console or directly call Graph API in embedded mode. And we can use the Gremlin, Graph Traversal Language, and REST API. Graph computations or metadata is stored in MySQL DB. Gravty uses Apache HBase as its main storage. It also runs Apache Phoenix on HBase for secondary indexing. The storage layer stores and reads data by accessing HBase. It is composed of a Phoenix repository and standalone memory repository. It has an abstract interface, so we can replace it with any other storage we want. The storage layer is linked with Kafka for event streaming. We all know how important a good data model is for a well-constructed database. There are various factors to consider when designing a data model. Today, I'm going to focus on table design in terms of table scan performance. Many graph database products choose to use a play-wide table model. This model clearly displays each edge is connected to a vertex. Vertex ID is used as a row key. Edges and properties are stored as a column. The problem with this model is that it has to scan columns and that it is not possible to split columns. When too many edges are added to a row, the row will excessively stretch out, becoming the victim of a hotspot. Gravty uses a Torero table. This table stores edges in a row and uses edge ID as a row key. It is composed of source vertex ID, a label for edge type, and target vertex ID. A Torero table is the better choice when using HBase because HBase splits a table by its rows. So this table can scan edges more efficiently and is better at parallel execution. This is a simple graph search query using a graph traversal language called Gremlin provided by Apache Tinkerpad. It queries the ID of the 3 users who are friends of Brown. As you can see, the syntax is very intuitive. Now, let's look more closely how the query is run in this model. In a flat-wide model, it requires one row scan to search for Brown and one column scan to search for Friend's edge. Depending on how columns are ordered, it may take a long time to complete the column scan. This is a Torero model used by Gravty. Since a row key is edge ID, the query can find what it is looking for with just one row scan. HBase splits a table by rows. This means you can move individual rows or a range of hot-spotted rows to a separate server. We can also perform parallel scanning. This is an example query that looks up friends of friends. Can you see the four square boxes? Each box is equivalent to the one depth query you just saw on the previous slide. The query runs 4 searches, 8 operations for flag white, and 4 operations for Toledo. In this way, Gravty keeps the number of scans as little as possible to reduce query execution time. Next is fine-tuning Gravty. Mr. Hoonmin will take it from here and talk about fine-tuning Gravty. Please welcome Mr. Hoonmin.
Hello, I'm Hoonmin. From now on, I will explain some of the adjustments we made to Gravty for better results. As I have a short time of 15 minutes, I will focus on a few crucial issues. The first one is making faster, compact graph calling. Think of graph traversal is composed of a series of sequential steps that are processed in a pipelined stream and uses Gremlin graph query language. This is an example of a graph traversal query for listing Brown's friends, ordered by their names, and fetching top 5 results. In this example, the query consists of 5 steps, where graph step and vertex step are followed by filter step and range step at mid-traversal. Since filter step and range step are query conditions, we merged them to the graph step and vertex step to reduce the number of steps. This is another sample query, but similar to the previous one, but slightly different. This query picks up 5 users among Brown's friends, ordered by their names, and deliver the results. First, outgoing edge step selects the targeted edge and returns to the incoming vertex step of the list of vertices that are connected to that edge. From the returned list of vertices, the incoming vertex step reads the name property of the vertices sequentially. However, Gravty does the reads concurrently in parallel. Also, Gravty preloads the property by reading them at previous step, thus reducing the query execution time. Depending on how row keys are created, HBase may suffer from region server hotspotting, where heavy loads of writes and reads occur. For example, if the value of a vertex ID increases by order of creation, too many writes can be pushed to one region server. Also, using sequentially ordered keys may cause inefficient region splitting, in turn will lead to inefficient use of storage. One way to solve the hotspotting issue is pre-splitting regions of a table based on workload estimation. Another simpler way is using Apache Phoenix feature, sorting table. What this feature does is that it automatically sorts the row keys with a prefix. In other words, adding a hashed prefix at start of original row keys. The new prefixed row keys can be used to distribute load evenly when writing to or reading from table. At first, we chose to use a sorting table, but then we met another performance issue. Gravty frequently executes select top end queries with limit clause. However, it turned out that the scan performance would drop if this query is run on sorting table. When the sorting table feature is enabled, a Phoenix client creates a query plan for parallel query execution. If a query has a limit clause, region server scans every region for the limited number of rows. When a limit clause is combined with ordering, the return result have to be sorted and merged on the client. Through performance testing, we concluded that this additional merge sort task decreases the query performance. So we decided to look for another solution. Our solution was to use both sorted table and pre-splitting. Firstly, we replaced the automatic sorting feature with our custom-built one by hashing the source vertex IDs. Second, we decided to pre-split regions as well. In this way, table regions can be pre-split at a given range of hash value, while still keeping the chunk of adjacent row keys ordered and grouped together. Testing showed that the performance increased by 3 times. Gravty creates an indexed graph view for faster graph search. To this end, secondary indexing is necessary. Because HBase does not support indexing, we decided to use Apache Phoenix. When you are adding Phoenix on HBase, we also added Kafka to make Phoenix handle index processing streams more efficiently. First, we changed the way Phoenix IndexCommitter works from synchronous way to asynchronous one. Secondly, we developed tools for failure recovery. This figure depicts how index processing streams flows between a Phoenix client and HBase region servers. By default, Phoenix IndexCommitter processes index updates synchronously. When a Phoenix client sends index updates to the target region servers, the Phoenix coprocessor performs the primary table updates first. If secondary indexes exist, the coprocessor performs index updates as well. During this time, multiple RPC calls are invoked between region servers. During the whole process happens transparently on the server side, so a Phoenix client has to wait until all index updates are complete. To reduce the number of RPCs, we decided to use Kafka and take more control over index processing streams. In case of Gravty, instead of sending index updates to target region servers, the Phoenix coprocessor sends them to Kafka. Afterwards, the indexers consume the requests in Kafka queue and send them to the target region server. In this way, Phoenix client can process the new index updates asynchronously without having to wait the previous updates to complete. Also, it can reduce the volume of RPC traffics between the region servers. The next 2 figures will show you how we change the workflow from the point of Phoenix client. By default, synchronous IndexCommitter returns a response to the client after all index updates are complete. On the other hand, an asynchronous IndexCommitter returns a response to the client right after sending index updates request to Kafka. After implementing asynchronous IndexCommitter, the server TPS tripled and region server connections became 1/8 of what it was before. Now, most requests can be processed within 10 milliseconds. one thing we should never forget is to prepare for failures. For example, index updates may partially fail, or a Kafka broker that stores index updates requests may stop running. Unfortunately, we cannot expect to recover everything back to a perfect state. However, we do have our policy for emergencies, which is fail fast and fix later. Gravty is designed to restart any request at any time. We made a tool that can replay all failed requests. Also, we developed our own time machine that can resume at certain runtime if a major outbreak occurs. We are working on automating the whole processes. We use various tools with Gravty for gathering and monitoring, visualizing performance metrics. For example, Prometheus for gathering data, and Grafana for our graph dashboard. We use Dravizud metrics and JVM exporter for Java system metrics. It's almost time to wrap up. Before we finish, KyoungBok will return to the stage and briefly mention our future plans.
Thank you, Hoonmin. Currently, single HBase cluster can serve a single graph. In the future, we plan to develop multiple HBase clusters that can be incorporated into a single graph. And we will add an HBase repository at the storage layer so that Gravty can directly access HBase without the help of Phoenix. Removing the Phoenix dependency will make Gravty run lighter and easier to control. Currently, only OLTP is implemented in Gravty. In the future, we will add OLAP functionality as well by implementing Tinkerpop Graph Computing API. One last thing, we will open source Gravty in the near future. And we hope we will have a chance to provide more technical details, such as performance test results, server specifications, and configuration details. Thank you for listening to the presentation.